All right. Hello, everybody. Welcome back in, and thanks for joining me. Welcome back to the channel. Today, we're going to be jumping back into Introduction to Algorithms, 4th edition. 4.6, Proof of the Continuous Master Theorem. Proving the Master Theorem, Theorem 4.1, in its full generality, especially dealing with the knotty technical issues of floors and ceilings, is beyond the scope of this book. This section, however, states and proves a variant of the Master Theorem, called the Continuous Master Theorem, in which the master recurrence 4.17 is defined over sufficiently large positive real numbers. The proof of this version, uncomplicated by floors and ceilings, contains the main ideas needed to understand how master recurrences behave. Section 4.7 discusses floors and ceilings and divide and conquer recurrences at greater length, presenting sufficient conditions for them not to affect the asymptotic solutions. Of course, since you need not understand the proof of the master theorem in order to apply the master method, you may choose to skip this section. But if you wish to study more advanced algorithms beyond the scope of this textbook, you may appreciate a better understanding of the underlying mathematics which the proof of this continuous master theorem provides. Although we usually assume that recurrences are algorithmic and don't require an explicit statement of a base case, we must be much more careful for proofs that justify the practice. The lemmas and theorem in this section explicitly state the base cases because the inductive proofs require mathematical grounding. It is common in the world of mathematics to be extraordinarily careful proving theorems that justify acting more casual in practice. The proof of the continuous master theorem involves two lemmas. Lemma 4.2. The proof of the continuous master theorem involves two lemmas. Lemma 4.2 uses a slightly simplified master recurrence with a threshold constant of n not equal to 1, rather than the more general n not greater than 0 threshold constant implied by the understated base case. The lemma employs a recursion tree to reduce the solution of the simplified master recurrence to that of evaluating a summation. Lemma 4.3 then provides asymptotic bounds for the summation, mirroring the three cases of the master theorem. Finally, the continuous master theorem itself, Theorem 4.4, gives asymptotic bounds for the master recurrences, while generalizing to an arbitrary threshold constant n not greater than 0 as implied by the unstated base case. Some of the proofs use the property described in problem 3-5 on page 72 and 73 to combine and simplify complicated asymptotic expressions. Although problem 3-5 addresses only big theta notation, the properties enumerated there can be extended to big O notation and big omega notation as well. Here's the first lemma. Lemma 4.2. Let A be greater than 0 and B be greater than 1 and be constants. And let f of n be a function defined over real numbers, n greater than or equal to 1. Then the recurrence, t of n, is equal to theta of 1 if n is between or equal to 0 and less than 1, as well as and recurrence if n is greater than or equal to 1 of the constant a times the recurrence t of n over b plus f of n, and has a solution, right? T of n equal to theta n to the power of log base b times a plus the sum for all values of j starting at 0 up to the floor log b of n, the a constant to the power of j times f of n over b to the power of j. Proof. Consider the recursion tree in figure 4.3. Let's look first at its internal nodes. The root of the tree has cost f of n, and at its a children, each with cost f of n over b. It is convenient to think of a as an integer, especially when visualizing the recursion tree, but the mathematics does not require it. Each of these children has a children making a squared nodes at depth 2, and each of the a children has a cost of f of n over b squared. In general, there are a to the power of j nodes at depth of j, and each node has a cost of f of n over b to the power of j. Now let's move on to the understanding of the leaves. The tree grows downward until n over b to the power of j becomes less than 1. Thus, the tree has height of the floor log base b of n plus 1. Because n over b to the power of that floor value of log base b times n is greater than or equal to n over b to the power of log base b times n, which is equal to 1. And n over b to the power of floor log base b times n plus 1 is less than n over b to the power of log base b of n, which equals to 1. Since we have observed the number of nodes at depth j is a to the power of j, and all the leaves are at depth floor log base b of n plus 1, the tree contains a to the power of log base b times n floor plus 1 leaves. Using the identity 3.21 on page 66, we have this new identity rearranged to equal big O of n to the power of log base b times a. Since a is a constant and a to the power of log base b times n floor plus 1 is greater than or equal to a to the power of log base b times n, which equals to n to the power of log base b times a, which equals to big omega of n to the power of log base b times a. Consequently, the total number of leaves is big theta of n to the power of log base b times a. Asymptotically, the watershed function. We are now in a position to derive equation 4.18 by summing the costs of the nodes at each depth in the tree as shown in the figure. The first term in the equation is the total cost of the leaves. Since each leaf is at the depth of floor log base b times n plus 1 and n over b to the power of log base b times n floor plus 1 is less than 1, the base case of the recurrence gives the cost of a leaf equal to big theta of 1. Hence, the cost of all big theta n to the power of log base b times a leaves is big theta of n to the power of log base b of a by problem 3-5D. The second term in equation 4.18 is the cost of the internal nodes, which, in the underlying divide and conquer algorithm, represents the costs of dividing problems into subproblems. As we'll see, the three cases of the master theorem depend on the distribution of the total cost across levels of the recursion tree. Case 1. The cost increase geometrically from the root to the leaves, growing by a constant factor with each level. Case 2. The costs depend on the value of k in the theorem. With k equal to 0, the costs are equal for each level. With k equal to 1, the costs grow linearly from the root to the leaves. With k equal to 2, the growth is quadratic, and in general, the costs grow polynomially in k. Case 3. The costs decrease geometrically from the root to the leaves, shrinking by a constant factor with each level. The summation in equation 4.18 describes the cost of the dividing and combining steps in the underlying divide and conquer algorithm. The next lemma provides asymptotic bounds on the summation's growth. Lemma 4.3. Let a be greater than 0 and b be greater than 1 and be constants. Let f of n be a function defined over real numbers, n is greater than or equal to 1, then the asymptotic of the behavior of the function is this. Defined for n greater than or equal to 1, and can be characterized as follows. If there exists a constant epsilon greater than 0, such that f of n is equal to big O of n to the power of log base b times a minus that epsilon, then g of n is equal to big O of n log to the power of log base b times a. If there exists a constant k that is greater than or equal to 0, such that, proving for big theta, if there exists a constant c in the range of 0 to c to 1, such that 0 is less than a times f of n over b, which is less than or equal to c times f of n for all n greater than or equal to 1, then g of n is big theta f of n. Proof. For case 1, we have f of n is equal to big O of n to the power of log base b times a minus epsilon, which implies that f of n over b to the power of j is equal to big O of n over b to the power of j to the power of log base b of a minus epsilon. Substituting into equation 4.19 yields this, which reduces down the last three series being geometric. Since b and epsilon are constants, the b to the power of epsilon minus 1 denominator doesn't affect the asymptotic growth of the g of n, and neither does the negative 1 in the numerator. Since b to the power of epsilon times the floor log base b times n plus 1 is less than this, equals down to big O of n to the power of epsilon, we obtain that g of n is equal to big O of n to the power of log base b times a, thereby proving case 1. Case 2 assumes this, from which we can conclude that this. Substituting into equation 4.19 and repeatedly applying problem 3-5c yields this down to here. The summation within the theta notation can be bounded from above as follows. Exercise 4.6-1 asks to show that the summation can similarly be bounded from below by omega log base b to the power of k plus 1 times n. Since we have a tight upper and lower bounds, the summation is this, from which we can conclude this, thereby completing the proof of case 2. For case 3, observe that f of n appears in the definition 4.19 of g of n when j is equal to 0, and that all terms of g of n are positive. Therefore, we must have g of n equal to big omega of f of n, and it only remains to prove that g of n is equal to big O of f of n. Performing j iterations of the inequality a times f of n over b, which is less than or equal to c times f of n, yields a to the power of j times f of n over b to the power of j less than c to the power of j times f of n. Substituting into equation 4.19, we obtain this, where big O of f of n. Thus, we can conclude that g of n is equal to big theta f of n. With case 3 proved, the entire proof of the lemma is complete. We can now state and prove continuous master theorem. Theorem 4.4, continuous master theorem. Let a be greater than 0 and b be greater than 1 be constants, and let f of n be a driving function that is defined on non-negative on all sufficiently large reals. Define the algorithmic recurrence t of n on the positive real numbers by t of n equals to a times t of n over b plus f of n. Then the asymptotic behavior of t of n, the recurrence, can be characterized as follows. If there exists a constant epsilon greater than 0, such that this equation, then t of n, the recurrence, is this equation. If there exists a constant k is greater than or equal to 0, such that this equation, then t of n is equal to this time theta bound. If there exists a constant epsilon greater than 0, such that big omega of this expression, and if f of n additionally satisfies the regularity condition, a times f of n over b, which is less than or equal to c times f of n, for some constant c less than 1 and all sufficiently large n, then t of n is equal to big theta f of n. Proof. The idea is to bound the summation 4.18 from lemma 4.2 by applying lemma 4.3, but we must account for lemma 4.2 using a base case for 0 to n to 1. Whereas this theorem uses an implicit base case for 0 to n naught, whereas n naught is greater than 0 is an arbitrary threshold constant. Since the recurrence is algorithmic, we can assume that f of n is defined for n greater than or equal to n naught. For n greater than 0, let us define two auxiliary functions, t prime of n, which is equal to t of n naught times n, and f prime of n, which is equal to f of n naught times n. We have t of prime of n, which equals to this, also equals to theta of 1 if this is true, this expression if this is true, theta of 1 if this is true, and this expression if this is true. We have obtained a recurrence for t prime of n that satisfies the conditions of lemma 4.2, and by that lemma, the solution is t prime of n is equal to big theta of n to the power of log base b times a plus the sum of this, right, from these values for j. To solve t prime of n, we first need to bound f prime of n. Let's examine the individual cases in the theorem. The condition for case 1 is f of n is equal to big O of n to the power of log base b times a minus epsilon for some constant epsilon greater than 0. We have this. Since a, b, and n naught and epsilon are all constant, the function f prime of n satisfies the conditioned case of the function f prime of n satisfies the conditions of case 1 of lemma 4.3, and the summation equation 4.18 of lemma 4.2 evaluates to this. Because a, b, and n naught are all constants, we now have t of n is equal to big theta n log b a, right? Thereby completing case 1 of the theorem. The condition for case 2 is f of n is equal to big theta n to the power of the, right, is this, for some constant k greater than 0 or equal to 0. We have f prime of n, which reduces down to here by eliminating constant terms. Similar to the proof of case 1, the function f prime of n satisfies the condition of case 2 of lemma 4.3. The summation in equation 4.18 of lemma 4.2 is therefore big theta, right, of this expression, which implies that the recurrence t of n is equal to this. which proves case 2 of the theorem. Finally, the condition for case 3 is f of n is equal to big omega of this for some constant epsilon greater than 0, and f of n additionally satisfies the regularity condition for all n values greater than or equal to n naught, and for this to be true. The first part of case 3 is like case 1, right? F prime of n equals to this, which reduces down to here. Using the definition of f prime of n and the fact that n naught times n is greater than or equal to m naught, right? For all n greater than or equal to 1, we have for n greater than or equal to 1 that this is equal to c f prime of n. Thus, f prime of n satisfies the requirement for case 3 of lemma 4.3, and the summation of inequality 4.18 of lemma 4.2 evaluates to big theta f prime of n, yielding t of n equals to big theta f of n, which completes the proof of the case 3 of the theorem and thus the whole theorem. 4.7. Akra-Bazzi recurrences. This section provides an overview of 2 advanced topics related to divide and conquer recurrences. The first deal with technicalities arising from the use of the floors and ceilings, and the second discusses the Akra-Bazzi method, which involves a little calculus for solving complicated divide and conquer recurrences. In particular, we'll look at the class of algorithmic divide and conquer recurrences originally studied by M. Akra and L. Bazzi. These Akra-Bazzi recurrences take the form of t of n is equal to f of n plus the sum of, for values of I equal to 1 up to some value of k, a sub I times t of n over b sub I, where k is a positive integer. All the constants a1, a2 up to a sub k are within, right, the set of real numbers and are strictly positive. All constants b1, b2 up to bk are within the set of real numbers and are strictly greater than 1. And the driving function f of n is defined on sufficiently large non-negative reals and is itself non-negative. Akra-Bazzi recurrences generalize the class of recurrences addressed by the master theorem, whereas master recurrences characterize the running times of divide and conquer algorithms that break a problem into equal-sized subproblems, modulo floors and ceilings. Akra-Bazzi recurrences can describe the running time of divide and conquer algorithms that break a problem into different size subproblems. The master theorem, however, allows you to ignore floors and ceilings, but the Akra-Bazzi method for solving Akra-Bazzi recurrences needs an additional requirement to deal with floors and ceilings. But before diving into the Akra-Bazzi method itself, let's understand the limitations involving in ignoring floors and ceilings in Akra-Bazzi recurrences. As you're aware, algorithms generally deal with integer-sized inputs. The mathematics for recurrences is often easier with real numbers, however, than with integers, where we must cope with floors and ceilings to ensure that terms are well defined. The difference may not seem to be much, especially because that's often the truth with recurrences, but to be mathematically correct, we must be careful with our assumptions. Since our end goal is to understand algorithms and not the vagaries of mathematical corner cases, we like to be casual, yet rigorous. How can we treat floors and ceilings casually, yet still ensuring rigor? From a mathematical point of view, the difficulty in dealing with floors and ceilings is that some driving functions can be really, really weird. So it's not okay in general to ignore floors and ceilings in Akra-Bazzi recurrences. Fortunately, most of the driving functions we encounter in the study of algorithms behave nicely, and floors and ceilings don't make a difference. The polynomial growth condition. If the driving function f of n in equation 4.22 is well behaved in the following sense, it's okay to drop floors and ceilings. A function f of n, defined on all sufficiently large positive reals, satisfies the polynomial growth condition if there exists a constant n caret which is greater than 0, such that the following holds. This definition may be one of the hardest in this textbook to get your head around. To a first order, it says that f of n satisfies the property that f of theta of n is equal to big theta of f of n. Although the polynomial growth condition is actually somewhat stronger, see exercise 4.7-4, the definition also implies that f of n is asymptotically positive, see exercise 4.7-3. Examples of functions that satisfy the polynomial growth condition include any of the functions of the form f of n is equal to big theta of that expression, where alpha, beta, and gamma are constants. Most of the polynomial bounded functions used in this book satisfy the condition. Exponentials and superexponentials do not. See exercise 4.7-2, for example, and there also exist polynomial bounded functions that do not. Floors and ceilings and nice recurrences. When the driving function in Akra-Bazzi recurrence satisfies the polynomial growth condition, floors and ceilings don't change the asymptotic behavior of the solution. The following theorem, which is presented without proof, formalizes this notion. Theorem 4.5. Let T of n be a function defined on the non-negative reals that satisfies recurrence 4.22, where f of n satisfies the polynomial growth condition. Let T prime of n be another function defined on the natural numbers also satisfying the recurrence 4.22, except that each T of n over b sub I is replaced with either the ceiling or floor of that value. Then we have T prime of n equals to big theta of T of n. Floors and ceilings represent a minor perturbation to the arguments in the recursion. By inequality 3.2 on page 64, they perturb an argument by at most 1, but much larger perturbations are tolerable. As long as the driving function f of n in recurrence 4.22 satisfies the polynomial growth condition, it turns out that replacing any term T of n over b sub I with T of n over b sub I plus h sub I of n, where the absolute value of h sub I of n is equal to big O of n over the log of the power of 1 plus epsilon times n. For some constant epsilon is greater than 0 and sufficiently large n leaves the asymptotic solution unaffected. Thus, the divide step in a divide and conquer algorithm can be moderately coarse without affecting the solution to its running time recurrence. The Akra-Bazzi method. The Akra-Bazzi method, not surprisingly, was developed to solve Akra-Bazzi recurrences 4.22, which by dint of Theorem 4.5 applies in the presence of floors and ceilings or even larger perturbations, as just discussed. The method involves first determining the unique real number p such that the sum of I equals 1 up to some value k of a sub I over b sub I to the power of p equals to 1, such a p always exists. When p is approaching negative infinity, the sum goes to infinity. It decreases as p increases. And when p approaches infinity, it goes to 0. The Akra-Bazzi method then gives the solution to the recurrence as this. As an example, consider the recurrence T of n is equal to T of n over 5 plus T of 7n over 10 plus n. We'll see the similar recurrence 9.1 on page 240 when we study an algorithm for selecting the ith smallest element from a set of numbers. This recurrence has the form of equation 4.22, where a sub 1 equals to a sub 2, which equals to 1, b sub 1 equals to 5, b sub 2 equals to 7 over 10, and f of n equals to n. To solve it, the Akra-Bazzi method says that we should determine a unique p satisfying 1 over 5 to the power of p plus 7 over 10 to the power of p equals to 1. Solving for p is kind of messy. It turns out that p is equal to 0.83978. And so on. But we can solve the recurrence without actually knowing the exact value for p. Observe that 1 over 5 to the 0 plus 7 over 10 to the 0 is equal to 2, and 1 over 5 to the 1 and 7 over 10 to the 1, sum to those together is equal to 9 over 10, and thus p lies in the range of 0 to p to 1. That turns out to be sufficient for the Akra-Bazzi method to give us a solution. We'll use the fact from calculus that if k does not equal to negative 1, then the integral x to the power of k dx is equal to x to the power of k plus 1 over k plus 1. With k equals to negative p, which is not equal to negative 1, the Akra-Bazzi solution 4.23 gives us this, which reduces down to big theta of n for t of n. Although the Akra-Bazzi method is more general than the master theorem, it requires calculus and sometimes a bit more reasoning. You also must ensure that your deriving function satisfies the polynomial growth condition if you want to ignore floors and ceilings, although that's rarely a problem. When it applies, the master method is much simpler to use, but only when subproblem size are more or less equal. They are both good tools for your algorithmic toolkit. Alright, this brings us to the exercises and problems for the end of the chapter here. This one was pretty brutal. Chapter 4 about divide and conquer algorithms. Right, everybody, this was Chapter 4, Divide and Conquer, from Introductions to Algorithms, CLRS, 4th edition. I hope you enjoyed this read aloud. Thank you guys so much for watching. I'll see you in the next one.